far into biochemistry, we need to address the elephant in the room, water. It's everywhere, it's super important, it's going to influence all sorts of things in biochemistry. We're talking hydrogen bonds, hydrophobic effect, intermolecular forces, all that good stuff. Let's dive in.
The importance of water starts with the fact that there's just so much of it. The concentration of pure water is about 55.5 molar, which is way higher than the concentration of basically anything we'll ever talk about in this class. If you want to put some numbers on it, that's about 33 septillion or trillion molecules per liter. So there's water everywhere, and well, water is kind of special. Water is highly polar. Because that oxygen is much more electronegative than the hydrogens, it's going to pull the shared electron density towards it, leading those oxygens to be partly negative and those hydrogens to be partly positive. When you have opposite charges, even if they're only partial charges, they're going to attract to one another. And so the partial positive of one water molecule is going to be attracted to the partial negative of the another water molecule. And what you're going to get is that these water molecules are going to be very sticky to one another, as well as sticky to other things that have partial or full charges. We'll talk more about how these can actually form this special kind of dipole interaction that we refer to as a hydrogen bond. But this is what it's coming from. It's just this dipole interaction where you have this dipole moment in each of these water molecules where the oxygen is going to be partly negative and the hydrogens are going to be partly positive. And this makes the water molecules want to bind to one another. Well, this has consequences for when you try to get something else to dissolve in water. So water is like our universal solvent. It's what everything in our cells and everything in our bodies is dissolved in, but not everything is equally water soluble. And so water is very picky about what it lets into its network. So water is going to want to form bonds to itself, or it's going to want to form these bonds. And when I'm talking about bonds, we're just talking about intermolecular attractions here, not like covalent bonds. These are all just non-covalent, but just more like partial charge attractions through those dipole moments or through the water's dipole and a charged molecule, say. So if you put in something that water likes, we call those things hydrophilic. And so hydrophilic things would have things like a partial charge or a full charge. But if you have something that doesn't offer something like that, something non-polar, something like a pure hydrocarbon, well, water's not going to want to let it into its network. And we'll see later how this can lead to this thing called the water exclusion effect. But basically, we can think about the properties of water as influencing what will and will not dissolve. Because in order for something to dissolve, you don't only have to form new interactions to it, but you also have to break up those water-water interactions. So let's talk a little bit more about these water-water interactions and how we can see kind of similar interactions in other types of molecules. This special type of dipole-dipole interaction that we're talking about, we call a hydrogen bond, or we often abbreviate this H bond. And often when we're talking about H bond, we typically draw these as dashed lines, like something like that. So we're not going to draw them as solid lines. They're not like a covalent bond, but they're also not just your normal partial charge attraction. They're a lot stronger. They actually have a slight covalent proportion. They're about like 10% covalent. Basically, what happens is that because that oxygen, or as we'll see, that nitrogen is so electronegative, it's going to pull the electrons towards it. And because hydrogen is going to be so small, you're going to get these short bond distances, and therefore you're going to get these really strong, weak bonds, we'll say. So what is the requirements for a hydrogen bond? Basically, you need a donor and you need an acceptor. And when we're talking about a donor, we're talking about a hydrogen donor. So when we're talking about this hydrogen donor, we need a hydrogen that's bound to something electronegative. And so we're going to have something that is electronegative, pulling the electrons away from the hydrogen and making that hydrogen partly positive. And so typically what you're going to see for this is you're going to see a hydrogen attached to an oxygen or a nitrogen. And so often what you're going to see is you're going to see an alcohol or you're going to see an amine group. And so when we're looking at this, In this diagram down here where I have the blue is this blue arrow. So basically on the bottom here, you're seeing the donors. And so we have an example here. We have a hydroxyl group. We have another hydroxyl group, another hydroxyl group. We have an amine group and another amine group. So all of those are ways that are contributing to that hydrogen, to that donor contributing that donation of that partly positive hydrogen. Now, in order for that partial positive hydrogen to form a hydrogen bond, well, it needs an acceptor. And so this is going to be our H bond acceptor. Now, what you want for an acceptor is basically the exact opposite. You want something that's electronegative, but you don't just want it to be electronegative, you also want it to have a lone pair of electrons. So it's not just electronegative, it actually has to have that lone pair of electrons. And so this can influence, say, if you had an electronegative atom that had its lone pair already in use. Now that acceptor, what it's going to do is it's going to hog electrons because it's electronegative. So it's going to be partly negative. And that's where we get our partly negative that's going to be attracted to the partly positive. And where can we find this? Well, we can find this typically on a nitrogen or an oxygen. So before we were talking about an oxygen or a nitrogen, but importantly, we were talking about the hydrogen that was attached to it. And now we're talking directly about that nitrogen or oxygen itself, and we're talking about the lone pair of electrons on it. Water is like our classic example, because in this example, well, you have these two groups that can act as our acceptors. And you have these two groups that can act as our donors. And so for each water molecule, you can form up to these 4 hydrogen bonds. And so these could be with other water molecules, or they could be with other molecules, such as those amide bonds, such as those carbonyl groups. In solid water, so in ice, you typically do have those like four bonds per water molecule. But in liquid water, you typically have, in liquid water, about 3.4 H bonds per water. And this is because, we'll talk about this in a minute, these bonds, although they are stronger than most dipole-dipole attractions, they're still relatively weak, and they're on the order of magnitude of the thermal energy of the water. So these are going to be constantly being broken and reformed. So this water is moving around all over the place, and it's not typically just like held in place with 4 other water molecules. Although you'll see in certain cases, water can be very tightly held and can form important roles, such as in the active sites of enzymes, you can get like structured water. Or around nonpolar things, the water molecules, they can't form the four because they have to have some facing the nonpolar thing, but they're going to try to maximize their water-water interactions elsewhere, and therefore won't be able to move all over the place. And so we'll look at that in a minute. In addition to between water molecules and between water molecules and other molecules, you see hydrogen bonds in a lot of places in biochemistry, and there are a couple that are going to be kind of like the most consequential. One is going to be in the base pairing between strands of DNA and RNA. So we have our 4 or 5 nucleobases, and each of these offers opportunities with hydrogen bond acceptors and donors, and they match one another. So you get this like specificity between the strands where you have an A binding to a T or an A binding to a U in the case of RNA, and then you have a G binding to a C. And so this specific binding comes because they have this distinct arrangement of donors and acceptors that are in the perfect kind of geometry for this to happen. The other important place you'll see it is in the peptide backbone. So in that, when you have those amino acids link up, what happens is you get these amide bonds, and we'll talk a lot about these amide bonds. But basically what you're left with is in the backbone of the peptide, you have an acceptor in the form of these, the carbonyl. So you have an oxygen with 2 lone pairs, so that's 2 places you can have acceptors, and you have a hydrogen on the nitrogen. So you have a donor here. Okay, so you might be wondering, well, what about this lone pair on this nitrogen? Well, this lone pair on this nitrogen is actually going to be involved in resonance. And so we'll talk a lot about this. But basically, this is out of commission. This nitrogen, this lone pair, involved in resonance. So we cannot use it for an H bond acceptor because it's going to be shared between that with the oxygen. Could write a resonance structure where basically we have COO, and I'm just going to do this abbreviated. But what we can think about is if we do this, we can push this. And now what we get is something that looks like that. So basically you have this resonance happening in the peptide backbone. In order to actually use that lone pair, you'd have to give up the resonance, and resonance makes molecules happy. And so they're not going to want to do that. And so you can't use that as as an acceptor, but you can use this hydrogen as a donor. And we're going to see that because you have this regularly interspersed pattern of these acceptors and these donors in the peptide backbone, what you get is these characteristics, what we call secondary structures of proteins, things like alpha helices and beta strands, which are where the proteins are going to kind of fold up in order to maximize those hydrogen bonding opportunities. Now, the reason why you get these distinct shapes and not just random blobs from these hydrogen bonds is because hydrogen bonds, they have special requirements. So we talked about how you need to have the hydrogen on something electronegative, and you need to have a lone pair on something electronegative. But you also have to have a couple of other specific things. So one is that for them to be strongest, you need everything to be in a line. So you need your donor to be in a line with the lone pair of your acceptor. And so if this is not at the right angle, the bonds are going to be much, much weaker. And so this is going to help explain how we can get those characteristic structures. In addition, these bonds are going to be like shorter than your typical intermolecular interaction. So they only work over like this short distance. And so between having the short kind of like defined distance and having that specific geometry, you can get these specific structures. And so these bonds are typically on the order of about 3 angstrom. So an angstrom equals 0.1 nanometers. So if we're talking about 3 angstrom, so what we're going to be talking about is about 0.3 nanometer long in terms of the length of these bonds. And so often in biochemistry, we're going to be talking in terms of angstrom because that's the typical order of magnitude that we're talking about in typical bond length. So angstrom is a really useful tool to measure. And when we talk about things like resolution, we're going to be talking in terms of angstroms. So if you had a 3 angstrom structure, say, it would be saying that you could tell apart things that were 3 angstrom apart. Okay, so this distance is going to be about twice as long as a carbon-carbon bond, a few times longer than a carbon-hydrogen bond, and we're talking about like covalent bonds. So in here, we're talking about a mostly non-covalent bond. So it's going to be longer than those covalent bonds. So it's going to be longer than a CH bond, but it's still not as long as if they were just, if they weren't in this bonding interaction. And so you get about 10% covalent character in these hydrogen bonds, but it's mostly non-covalent character. And we're just gonna classify them as non-covalent bonds. How strong are these bonds? Well, individually, they're pretty weak. So individually, they're fairly weak. So they're about on the same order of magnitude as the thermal energy. And so what this means is that they're going to have a very short lifetime because the molecules kind of have that much energy just kind of randomly, so they can randomly break off from one another. And so the average lifetime of a single hydrogen bond is going to be only about 1 to 20 picoseconds. But, so this is single one. And typically we don't just have one. So if we look at that peptide backbone, we had all those different opportunities for hydrogen bonding. And so we normally have lots. but we have lots. And so even though the individual hydrogen bonds might be breaking off continuously, and if you have just like free water, those water molecules are going to be sliding all over the place. If you have something like a protein backbone where you have all that ordered water, not ordered, but you have all those hydrogen bonding interactions in that backbone, what's going to happen is that, say, one of those bonds randomly breaks. Well, the whole molecule is not going to fall apart because you have all these other interactions. And so sometimes we talk about kind of like molecules breathing, where those hydrogen bonds kind of just like break, but then they reform. So it's not like you're totally losing the structure. If you're interested in this, there's actually a topic called, there's a technique called hydrogen deuterium exchange mass spectrometry, which actually takes advantage of kind of this breathing and kind of like measuring how the secondary structure formation of proteins, the more stable it is, the less likely those hydrogen bonds are to kind of like break off. And therefore you can measure the exchange of those hydrogens for deuterium and therefore measure kind of the flexibility and various things about the molecule. So it's a technique that I use in grad school, and it's just something to know about if this sounded interesting to you and you want to look into it a little more, but we probably won't have time to get into it into this course. So we have these fleeting interactions. We said they're fairly weak individually, but collectively they're strong, and they're going to be stronger than most non-covalent interactions. Except for salt bridges. So except for like ionic bonds, depending on the dielectric. So basically, if you have a high dielectric, if you have something with very polar, if you have a lot of salt, those ionic bonds are going to be weaker. And therefore, the strength of those hydrogen bonds are going to kind of increase in importance. And so we'll look at that when we think about what bonds, ionic bonds on the surface of a protein versus inside of a protein, and things like this. But for the most part, we think about these hydrogen bonds as being weaker than those ionic bonds, but stronger than most of the non-covalent bonds that we're going to talk about. So let's talk a little bit more about what some of these non-covalent bonds that we're talking about are. So at the heart of it, they kind of all just involve this basic idea that opposite charges attract and like charges repel. So if we're talking about ionic bonds, which we often call these like salt bridges, because if you have something positive and something negative that cancel each other out, we call that a salt. And so this is an example of a salt bridge. We'll see these a lot when we talk about the charged amino acids. And so these salt bridges can form, that would be this would be an ionic bond. But we could also have these partial charge attractions, and we have different names for these depending on whether they're like permanent or non-permanent, whether they're induced, this sort of thing. And so collectively, we can call all these non-covalent interactions intermolecular forces. So intermolecular forces are going to be our non-covalent interactions. So remember that when you have inter means between. So we're talking about interactions between molecules, and by definition, this means that they're not covalently bonded. Something that is a molecule is made up only of covalent bonds, but if you have interactions between those molecules, then those are going to be non-covalent interactions. And so with ion-ion, we talked about this would be our ionic bonds. And we're talking about side chains and things. We often call these salt bridges. When we're talking in the contents of like proteins, amino acids. We can have a permanent dipole. So an example of this would be our hydrogen bonds that we just talked about. So those water molecules are always going to have that dipole. And so they're always going to be able to form these interactions. We also said that water can form interactions to full charges. So what you can get is you can get an ion permanent dipole interaction where, say, if you dissolved a salt in water, well, now those water molecules are going to hang out with that salt ion. Now we'll see too that this can kind of take the water out of commission in terms of binding to other things. So this can lead to an increase in the kind of importance of non-covalent bonds, of like what we were going to call like van der Waals interactions and things like this. So let's talk about those. Basically, what can happen is you can get induced dipoles. If the charge, because you have electrons moving randomly about, and whizzing around that central nucleus in kind of like an electron cloud, if there randomly happen to be more on one side than another, well, then you get a partial charge. You get a temporary dipole. And so this can happen just randomly. And so what you get like these London forces or these dispersion forces where you kind of get this like instantaneous dipole. And then that instantaneous dipole can kind of attract the thing next to it. And this can kick off a chain reaction where you get the molecules forming this kind of temporary strengthened network. But if one of those depolarizes, then this whole thing breaks. So these can be very weak. Somewhere in between, what you can get are like induced dipoles from things like another dipole or things from an ion. So these would be dipoles that are induced by something, but they're not just like randomly happening. So you can get these induced dipoles. But in all of these cases, we're just talking about this partial charge separation. The more the separation is, the more that the difference in the charges, the stronger the effect is going to be. But these all have the same kind of idea at their heart. So we have that water can form those hydrogen bonds. Water can form interactions with ions. Water can form interactions with temporary dipoles. So water can make lots and lots of these interactions. But in order to make interactions to things other than water, well, it has to break off its interactions with the water molecules. And so whether something dissolves depends not only on whether water wants to make interactions with it, or water likes making interactions with it, whether it can make interactions with it, but it also depends on whether it's worth it to swap its water interactions for those solute interactions. And so if it is, then the thing will dissolve. And if it isn't, then the thing won't dissolve. So what determines this is going to be, at its heart, we can think about this in terms of thermodynamics. And so when we're talking about thermodynamics, we're talking about our delta G, our change in free energy. And so remember, we want that delta G to be negative for things to be favorable. And the way that we can make that something would be favorable is if the products had a lower enthalpy. So if they had more stable bonds, if they had like more and more stable bonds. So remember, enthalpy, we're thinking about bonds. And then with entropy, we're talking about randomness or disorder. So what happens when something binds is you have to take into account, okay, so we broke off those water-water bonds, and now we're forming new water solute bonds. Are those bonds more stable than the water-water bonds? And if so, then you're going to get a negative enthalpy, and that's going to be favorable. But if not, you're going to have a positive enthalpy. But even if you have that positive enthalpy, not all hope is lost because you still have entropy. And whether or not you have entropy is going to depend on kind of how much of the water, how free those water molecules are and how free the solute molecules are compared to what they were before. And so to illustrate this, let's talk about something called the hydrophobic effect. And so basically, if you think about water and it's just hanging out, if there is something nonpolar that comes in, what's going to happen is those water molecules are going to have to give up their water-water interactions, and they're going to have to kind of form interactions with this thing that they don't want to form interactions with. So they can't form any of those. The only thing that they could form with something nonpolar would be those instantaneous dipole, those like dispersion forces, those van der Waals forces. And so instead, the water wants to maximize the better forces that it can form and wants to maximize its water-water interactions. And so although before we talked about when we had like bulk water, it's moving all around and it's forming all those interactions with water. In this case, the water molecule is kind of going to cinch around the nonpolar thing. It's going to maximize its water-water interactions and minimize the interactions with that nonpolar thing. So this nonpolar thing is going to be excluded. What this is doing is it's taking these water molecules, though, that were all happy, they were all roaming around, and now it's kind of locking them in place. So what you're getting is a lower entropy. But what would happen if those molecules were now joined together? If those molecules were joined together, it takes fewer of the water molecules to surround them. And so in this way, by kind of combining those nonpolar things, clumping them all together, less of the water is taken out of commission. So you have more of the water molecules that are going to be free, and this is going to make it so that you have an increase in entropy. So you get more of the freed water when you group the hydrophobes together. And this is the basis for something called the hydrophobic effect. And so this is also called the water exclusion effect, because water is excluding those things. And so when we talk about phobic stands for fear, but I think that's misleading. Because it's not that these things are afraid of water, and it's not even that they're avoiding water, it's that the water is avoiding them. And it's this water avoiding them, this water excluding them, that is going to force them together. This has important consequences, though, because once they're forced together, they're actually going to be able to form some interactions. And we often call these like hydrophobic interactions. But remember that this is the same sorts of interactions that we can see before. And in this case, the only thing those nonpolar molecules can do is that they're going to be able to form those instantaneous dipoles. You're going to get those like dispersion forces and stuff like this. So this would be the basis of, say, your quote unquote hydrophobic bonds, but there's really not a hydrophobic bond. Instead, we're talking about water excluding these things getting clumped together. And then if one of them happens to randomly depolarize, then you're going to get these chain effects. And so you can get these individually weak, but collectively strong interactions of these nonpolar molecules inside of the water network. Now, what's going to happen is typically you don't just have a fully nonpolar molecule. You're going to have something that has nonpolar and polar parts. So something that's like amphiphilic. So if you have your water out here and you have your water out here and stuff, what's going to happen is your molecules are going to line themselves up so that their polar parts are going to hang out with the water and their nonpolar parts are going to hang out away from the water. And so it's most easy to see this in the case of like a lipid, or I mean like a soap, where you have a positive head, or you have some sort of hydrophilic head and a hydrophobic tail, and those are going to be in the water. And so you get something called like a mycel. And some cases where you get something like a bubble. But all of those things are going to be optimizing those water-water interactions and minimizing the water nonpolar thing interactions. It's not always quite as obvious as this, but in the case of something like a protein, you do still have nonpolar and polar parts. And so in a protein, it's going to arrange itself so that the polar parts on the outside and the nonpolar parts are on the inside. And we're going to see this. We're going to see this a lot more with better illustrations. But this is a key force to protein folding, is that you have these different amino acids. Some of them are very hydrophobic, so water is going to exclude them. Some of them are hydrophilic, so water is going to let them into its network. And this is going to be the main driving force of protein folding. And we'll get more into that later in the course, but it's just, this is all coming from that water exclusion effect, from that hydrophobic effect that, remember, is caused by the water kind of trying to maximize its own entropy and its own favorable interactions. When you're thinking about the hydrophobic effect, I want you to think entropy, because Remember those it's forming less favorable interactions, but you have this increase in the entropy of that solvent. So this can get kind of confusing if you're thinking about, say, a drug binding. So you might be thinking, okay, well, if something's binding, you're going to get a decrease in the entropy, right? Because things are going to be held down more. You have less rate to move, less freedom for movement. But it's those solvent molecules that you need to take into account when you're deciding whether something is actually going to be entropically favorable in this case. So what we're actually going to see is that in a lot of cases, you'll have some sort of drug molecule that often one of the biggest hurdles for drug manufacturing is that the drugs are not very water soluble, so it's hard to get them into cells. And the reason why these drugs are often not very water soluble is because they often bind to fairly hydrophobic patches on a protein or on some other molecule. And so that when they bind to those hydrophobic patches, well, now what they're going to do is it's kind of like taking something like this, where you have all these water molecules that are taken out of commission by surrounding that hydrophobic patch. And now if you kind of replace that with something else, then you're able to free up those water molecules. And maybe the hydrophilic parts, like the polar parts of those molecules, can then form interactions with the water. So you're kind of able to exchange out some non-favorable interactions for more favorable ones and free the water. We'll also talk about when in the context of enzymes. So these are often proteins, sometimes proteins and nucleic acids that are going to help speed up reactions in various ways. And we'll talk a lot about different mechanisms enzymes can use. But one of them is that they can like desolvate active sites. So basically, sometimes you can get a solvation shell. So like what we talked about before, how the water is kind of clinched around something and hiding it. This can hide important active sites on enzymes, making it difficult or impossible for reactions to occur. What enzymes can do is one thing that they can do is they can help remove that water coat, but keep the substrate soluble by kind of like replacing bonds to water with bonds to the enzyme. And so there are different places that we'll see kind of solvation come into account, and swapping interactions with water to swapping interactions with other molecules. And finally, we need to talk a little bit about water. It's not just water, or I mean, it's not just H2O. It also auto-ionizes to give you a hydroxide ion and a proton. Although that proton basically, because remember we have that 55.5 molar water, that proton isn't just going to hang around. It's going to latch onto a water molecule to give you this hydronium ion. So in water, you're going to have this mix of water, hydronium ion, and hydroxide ion. But almost all of it is actually just going to be water. But there are very, very few ions in water. So by doing some calculations from the pH and the molarity of water, you can figure out that only about 2 in a billion molecules of neutral water are ionized at any point. But this ionization and proton swapping is happening all the time. So it's super duper fast. We're talking on the order of trillions of seconds. And so this is why we can have things like water acting in all sorts of reactions like ions of water acting in all sorts of reactions to catalyze things in acid and base mechanisms. And so we'll see this when we talk about things like enzymes. But we can think about there kind of being protons all over the place, being hydroxide ions all over the place, and these protons kind of jumping from molecule to molecule, even faster than diffusion. So it's actually pretty cool, and we'll see more about this later in the course. But for now, know the basics. Know that we have a lot of water, that this water is highly polar, that this allows it to form all sorts of partial charge attractions. It has a permanent dipole, so it can form those permanent dipole ion, permanent dipole, induced dipole, all of those good things we can form with these water molecules. Although one of the most common things we're talking about with water molecules is actually going to be our hydrogen bond. But this doesn't just happen between water molecules. It can also happen between the bases of DNA, between the backbone of a protein, all sorts of different places. And the precise geometry and length of these bonds makes it so that we can get distinctive structures. We'll talk more about how the individual amino acids, like their unique parts, their side chains or R groups, can influence exactly the angles that can take. And so influence whether they can be in an alpha helix or in a beta strand. But it's really the hydrogen bonding from that distinctly distributed combination of donors and acceptors that's going to make it so that all these different proteins can form similar secondary structures. And we'll get much more into this, but know that this is happening because of these hydrogen bonding interactions, where you have a lone pair on something electronegative, you have a hydrogen attached to something electronegative, you get this partial charge attraction, and then they're going to be strongest if they're in line. And if they're strongest at the shorter distances, and they're typically on the order of about 3 angstrom. Remember that individually, these are fairly weak. They're going to be stronger than your other types of like van der Waals forces and things like this, but collectively, they're very, very strong. But they're very short-lived because the strength of each one of them is only going to be on the order of magnitude of the energy of the molecules, just like random energy. So if you have just bulk water, it's going to be kind of all these water molecules are going to be moving around. And if these water molecules are tied up, well, this is going to decrease the entropy. We can increase the entropy again by forcing the hydrophobic things together and freeing up more solvent molecules. So this is the basis of the hydrophobic effect, this entropy driving it. And remember that there are some ions in water, and you can think about there kind of being always going to be some ions around to help you catalyze your reaction. But these, they're very few in terms of their absolute numbers, which is probably good because then they'd be causing things to happen all over the cells that we didn't want. So those are the basics of water. And in your practice sets and things, you'll get a lot more practice working with water. And throughout the course, you'll get a lot more hopefully gain more of an intuition about how water is going to affect or not affect biochemical processes.